So I'm going to take my shelling order and line all the simplexes up in the shelling order. And then for every facet j here, that is, everybody here, and for every previous facet I that comes before it, we can find a facet k that has the property that it's absorbing, in the sense that if we're looking at the intersection between I and j, it says, well, you don't need to worry about that because that's contained in the intersection between k and j. So this is the important one, and that one doesn't matter because any intersection of these two is inside the intersection of that one. And moreover, we want it to be maximal, meaning that if I throw out everything in a j that's also in k, there's only one vertex left. So that says that, in some sense, if you're looking at phi j and the intersection with what comes before, the intersection with phi k is all that really matters. We're going to do a lot of partial and total orders. So we're going to find something called face ordering. So I'm going to take a simplex, an arbitrary n simplex, and I'm going to take any face of it, of any dimension, and I'm going to represent it as a bitmap where I'm going to use 0 to mean present, because I want the entire simplex to be the minimal element. And so the entire simplex is all zeros, and any face is, I have a 1 here indicating that that vertex is left out. And we're going to use that bitmap as a way of inducing a kind of a lexicographic order on simplexes. So the maximal simplex is the least element in the order. And then given any two faces of the same dimension, we order them lexicographically, that is to say, arbitrarily. So then we prove that given a simplex, the k-skeleton is shellable. And I won't go over the details of the construction, just to say that we use that phi I, phi j, phi k construction. That is, given any phi j, we find, and any prior phi I in the order, we construct a phi j that has the properties that we want. And all we do is we check its maximal, check its absorbing, and this is all just looking at the representation with bit tweezers. Then we looked at pseudospheres. So here, remember, we have a set of n-1 process IDs, and this is important because a lot of the applications are going to be just unions of pseudospheres. Sequence of sets, 1 per process, they might be the same. A vertex is a process and an element from VI, a simplex. We have distinct process IDs and elements from each VI. And the idea is that we have all of these elements, these sets that we're using to decorate the vertexes, and we just assume that we have an arbitrary total order on all of those elements. And again, it doesn't really much matter what it is as long as we have one. And then we can use that to, if we use the face order induced by that, then that's a shelling order. And then all we did here was we just checked the details, which again I'm going to skip over because we did it already. So we check the different conditions, and then we're done. Okay, so then remember, a complex is pure if all the facets have the same dimension. Almost all of the complexes we're going to be looking at will be pure, so I won't repeat it too many times. I'm going to define a notion called the codimension, which says that if I have an m-dimensional simplex, then the codimension of that simplex in the complex is just the difference. And this is convenient because otherwise we would have lots of expressions with n minus m in them, which would be hard to parse. So you can think of the codimension as being the difference between the dimension of the simplex and the dimension of the complex where it lives. So for example, a facet has codimension 0. And remember, carrier map sends each simplex of x to a subcomplex of y.
So it's 0, not 1 for a facet?
The codimension is 0 for a facet because a facet has dimension n, and the complex has dimension n. And so the difference is 0. There's always a little bit of potential confusion because the number of simplexes is 1 off from the dimension. But here we're talking about differences where that doesn't show up. So a facet is codimension 0. So if you want to quickly parse a lot of the expressions, every time you see codimension, if you think about facet, just erase it. Okay, so this is the kind of main theorem that we use. We want to do inductive arguments, saying that if a model computation has a nice property, if you do it for 1 round, then we can inductively extend that for multiple rounds. And so I'm going to prove this in kind of a, well, actually we did prove this in a kind of abstract formal way, and then I'm going to go through specific examples to show you how this looks at message passing, how this looks in shared memory, and so on. But here I'm going to prove the theorem in all its abstract glory, and then explain how this applies to actual models. So here we have a carrier map that has the property, has a local property. It says that every simplex, the image of what it means to run the protocol for 1 round, starting here, is k minus codimension of sigma minus 1 connected. So for example, this is a facet, this vanishes, and this says that the image of a facet is k minus 1 connected for some k, because ultimately we're interested in showing that k-suit agreement will be impossible. And so we need the codimension because in order to apply nerve lemma and stuff like that, we need it to behave nicely in lower dimensions as well. And so that says that as sigma gets smaller, then the codimension gets bigger, and the degree of connectivity gets smaller at the same time. Okay, then if it satisfies this nice local property where the image of each simplex is this much connected, then the image of the entire complex is k minus 1 connected. So that says that if you run for 1 round, you have this nice local property, then you get this nice global property. Okay, and again, I'll skip the proof. It's an inductive proof. We use the fact that it's shellable. Actually, we don't use the fact that it's shellable just yet. But okay, then anyway, this is the. So what we did was we have an inductive argument where we look at we take the shelling order, we look at a prefix of it, we add one more thing, and then we want to show that the union of the two things is k minus 1 connected, so we show the intersection is k minus 2 connected, and then we're done. So the main theorem says that these kinds of maps compose. So here's our model of computation where we start out with a complex. We run our computation for 1 round, and that's a carrier map that takes each simplex and produces a subcomplex. We look at all of them, we get C1, which is the state after running it for 1 round, and then we keep running it all the way for as long as we want. And the theorem says that if the image of each simplex for 1 round is a shellable complex of this dimension, so in other words, if it's a facet, then it has to have a dimension at least k. Then the composition of all of them is this connected. Again, it's k minus 1 connected.
So this is shellable for every sigma
in any of the CI.
in CI.
Yeah. So so any simplex is a shellable complex of this dimension, which means it might be empty. If it's a small dimension and this is less than -1, then it's empty. And empty complex is trivially shellable as far as we're concerned. So that says that if you want to show that the complex is k minus 1 connected for a long computation, and we can break our computation up into small pieces, round by round pieces, that have this nice local property that the image of a single simplex is shellable, then we're okay. And what?
And then is it what's up and low is true for every sigma in C0?
Yes. Now typically we're going to start out with C0 being a single simplex, but it's true, but it doesn't have to be. So this says that if our goal is to show that a big computation can't solve k-set agreement, then and we can break it up into these nice round operators, then this says that all we need to do is worry about a single round operator. In particular, we need to show that this condition holds. So this says that we can, in some sense, take a microscope to our model of computation and just show that this one local property holds for a single round. And then as long as we can compose these rounds together, then we have our connectivity property.
And the sigma in the bottom box comes from C0.
Yeah. This is for any sigma in C0. The sigma here is in any CI. So they're different sigmas. Okay.
So you have two types of locality. One is the locality pair within each complex. You go kind of in the Schelling order, and then you have the locality or the incrementality of the computation that you go in iterations.
Oh, yeah.
So there are two ways that things are broken apart.
Yeah.
Taken apart.
Yeah. Yeah, so first you need to break your computation up into rounds.
But within each round, you also, what you proved before, also had a different kind of locality.
Yeah, what we proved before was it's actually a lemma that we need to prove this, for the induction step here. So this is the one that matters for our applications.
Sure.
So it says that if you can break it up into rounds that have this nice local property, then you end up with a long computation that has this nice global property.
But you also broke up the individual complexes into
Yeah.
in the Schelling order when you did the proof. So
Yeah.
it was another locality.
Yeah. And so the fact that all of these things happen to be shellable is, what gives us the nice structure that we can use to put all these things together. Yeah, so again, I'm going to skip the proof because we did it, but basically it's an inductive argument. We start at the back and we sort of induct forward, get longer and longer chains. So so we basically got here. So we proved this theorem in all of this kind of abstract generality that says that if your round by round operator has this nice local property, then we can string them together. And sometimes we can string them together forever to give us impossibility results. And sometimes we can only string these things together for a finite amount of time because the operator requires failing some processes. And eventually we'll run out of processes to fail. So typically in the asynchronous models, we can run forever. So asynchronous models give us impossibility results. Synchronous or semi-synchronous models, we need to crash processes in order to get the right properties. And eventually we're going to run out of processes to crash. So those turn into lower bounds on either time or around complexity. Okay, so now what I'm going to do is I'm going to look at a bunch of specific models. Most of the classical models from the literature, and show you that in fact this theorem applies. That is, turns out that in a natural way, these problems can be broken down into round by round computations, and the image of every simplex turns out to be shellable. And so in some sense, this is a statement about, says that shellable complexes can be found in the wild. That these models of computation existed before anybody noticed that shellability was relevant. And so it's kind of interesting that these things that people invented even long before people thought about using topology and simplicial complexes turn out to be shellable complexes. And I'm not quite sure why that is. So we're looking at an asynchronous model where there's no bound on the on the timing of steps. And we're looking at a message passing model where they send messages to each other.
Is that mail asynchronous message passing?
This is, beg pardon?
Mail.
Well, that's asynchronous over here with the heartbeats, and this is message passing because this is a message.
And you don't know how much time this mail will take to reach?
No.
This was bounded because the 15th of May 48
Was-
was no longer accepted in the post. So if you didn't get there, it would be lost.
But that's okay. So that's semi-synchronous model. Okay, so what does the adversary do here? What is our failure model? Well, we're going to look at an adversary that never actually fails a process. The thing is, the adversary could fail a process, so our algorithm has to work if the adversary fails a process, but we're only going to look at executions where it never fails a process, but it can delay them. It can delay the process.
So if you assume the adversary has no failures, why?
Oh, if you assume the adversary doesn't fail a process, then everybody could just wait for process 0, and then you could do consensus.
So you assume there are failures.
I assume that your algorithm has to work if failures happen. And now what I'm going to do, you can think of this as a kind of a game where the adversary says, I could fail processes. So you have to design an algorithm that works. The adversary comes back and says, aha, now when I run it, I'm not going to fail processes. And because you have to be prepared for the adversary to fail processes, even if it chooses not to, then the adversary can make your program run forever without the complex becoming k minus 1 connected.
So I don't see the difference between saying that the adversary can fail the process or that.
Oh, so what I'm saying is I'm going to, so the adversary could fail processes, but I'm going to consider executions where it doesn't. But because it's asynchronous, what the adversary can do is the adversary can take any process and just delay it long enough so that everyone else has to finish without ever hearing from them. And so if you knew the adversary wasn't going to fail a process, then you could wait for it. But you can't ever wait because the adversary might fail the process. And so given that, I'm going to see what happens if the adversary, there's a reason the adversary looks evil. It's because the adversary is now going to not actually fail the processes, but it's going to delay them in such a way that you can't tell the difference.
So somewhere inside the construction, there's a way to deduce an execution where no process fails.
Yeah. Because it's asynchronous.
Infinite run where no process fails, infinite execution where no process fails, and still nobody decides.
So what we're going to do is I'm going to say, you give me a finite protocol, so there's no infinite runs. But in that protocol, what the adversary can do is the adversary can kind of pretend to fail some and just stop them and not run everything. The others have to finish without waiting for the delayed processes because they might have failed. And then the adversary can then revive and run the remaining processes. But the lack of failure means that we can string the round operators together arbitrarily. Because if the adversary had to fail processes, then eventually it would kill them all, and then you couldn't run any further. But what I can say is, you give me you give me any finite number of rounds, and I will show you how the adversary can prevent your protocol complex from can keep your protocol complex highly connected for that number of rounds.
So if I understand right, the adversary can, you need an algorithm that even if someone fails, it needs to give some output sometime.
Yeah.
And if no one fails, then you need to give the right output.
Yeah. No, you even want to give the right output if somebody fails. So if you give an output, then it's got to be the right output. But what we're going to do here is I'm going to look at full information protocols where you send the maximum amount of information around, and anything you can do if you send around maximum information. So everybody just rebroadcasts their state to everyone. You collect everything you know about everyone. You rebroadcast that. Because we're interested in lower bounds, so we don't care that our messages are exponentially long and so on. And then in the end, what I'm going to say is the adversary has managed to make sure that your protocol complex is still k-connected, and therefore, or k minus 1 connected, and therefore you can't do k-set agreement in this model. And then we'll actually show that that's tight, that you can do, that there's a number for which you can do a k-set agreement and a k for which you can't.
This is in line with the proof that you did, you showed connectivity explicitly, where there were situations that in order to show connectivity, indistinguishability, or whatever you call it, you had to hide one process.
Yeah.
And then you were forced not to show up, not to let this process show up again, because these cannot be combined together.
Yeah. But here, what'll happen is that we can delay. the adversary will actually delay processes, but it never has to actually kill them, because we want to be able to keep the round by round protocol going for any finite amount of time. So it's not, technically it's not forever. It's, you give me a number and then I'll run for that amount. So the next thing is we're going to deliver the messages in FIFO order. So you don't need to worry about omission failures, out of order, whatever. But we're going to say, well, on round R, the adversary, because it's asynchronous, may choose to withhold the messages from you. But at any time, if it feels like delivering a message to you, if you're in round R, it may send you the round R messages, and at the same time it does that, it will send you all of the messages that have piled up. It's like my secretary in the United States sends me these big envelopes full of bills that show up at my office, and they all show up at the same time, even though they arrived asynchronously. So the idea is that on round R, you either get no messages or you get kind of all the messages that you had before. So here is what a protocol looks like in this model. So this is a generic full information protocol. You accumulate all the state you can, and then whatever problem you want to solve, you look at that state and then decide what you want to do. So initially, your state is just your input, whatever your input is, because that's all you know. Then on round R, what you do is you broadcast your previous round state to everyone. Then you wait until you get the round R messages from a survivor set. Remember, survivor set is any set of processes that might be the only living processes. So you can't wait for more than a survivor set because they might never show up. But it's always safe to wait until you hear from some survivor set. So like for wait-free computations, you can't wait for anyone because you might be the only survivor. But if you're T-resilient, then you can wait for n minus t plus 1 processes to show up, because more than that can't fail. So you wait for a minimum of messages to show up. And then your new state is just the concatenation of all the messages you received. So in some sense, all you're doing is you're just rebroadcasting everything that you've learned on every round. So this is a full information protocol. You can't, anything you can do with this kind of protocol. Okay, and then the idea is that since the messages might not be delivered in the same round, but the delivery is of FIFO, then we can ignore late messages. So in other words, all we need to worry about is that if we're in round R, then we worry about what happens when we get the round R messages. Because we're waiting for a survivor set, we're waiting for the round R messages from that survivor set. Yeah?
So FIFO would mean that each of the messages is actually stamped with the
With a round number, yeah. Yeah.
So they all get batched up. So
Yeah.
unless they're stamped, you cannot make out which was.
Oh, but since the messages what the messages are basically a history of everything you've seen, you could, in principle, deduce this must be round R because I've seen R levels of information in there. But it's easier to talk about it as if they were labeled with this information, even though it's sort of implicit in the structure. So you can think of this as sending large recursive list structures around. Okay, so what does round operator look like? So here it is in all its kind of fearsome generality. What does this say? Well, it says that each process, so it says that this is the set of processes that are actually participating, sigma. This is the asynchronous operator, so we'll call it R sub A, just so we know what it is. It's a pseudosphere where we take this sphere, every vertex here, and we decorate it with the messages it received. So it's a pseudosphere where the base is the sigma. What is it? What does each process get? Well, it gets the messages from a subset of the participating processes. So sigma are the ones that are actually alive. You can't wait for everyone in sigma to show up because you don't know who they are. All you have is your local information. So, but you can wait for a face of sigma, a subset of sigma, that includes a survivor set. So this is just rewriting in Greek letter notation the protocol that I showed you operationally on the previous slide. So it says that each process waits until it hears from a survivor set. What is the survivor set? Well, it's a face of the current simplex. So you're hearing from some of your neighbors in sigma, and so you just pick the ones that have survivor sets. And these can be done independently because the adversary can deliver one set of messages here and another set of messages there. That's why it's a pseudosphere. It's because it's everybody can independently get one of these values. So you look at all the different ways you can combine them. Another way to say that is each vertex of sigma is labeled with a face of sigma containing the survivor set. So this is just a kind of a more compact way of writing what's going on here. So the theorem says that for any simplex sigma, the image of sigma is shellable of dimension at least C minus codim sigma minus 1, where C is the size of the minimum core for that adversary. Remember, core is a set of processes that can't all fail. Okay, so what it says is that if the codimension is less than C, that is, the number of processes you don't hear from is less than C, then this is non-empty. In fact, it's a dimension sigma pseudosphere. And we proved 2 weeks ago that pseudospheres are shellable, using the face order and so on. So that's shellable as long as the codimension of sigma is less than C. If the codimension of sigma is greater than C, then it may be that you don't hear from everyone. And it may be, maybe you do, maybe you don't, but we don't care what happens in those dimensions. All we care about is that the dimension is big enough, and that gives us the connectivity result that we want. So we just need to check that the dimension of sigma is greater than C minus its codimension minus 1, which is just a symbol pushing. So that we want to show that this is true. We move things around. The dimension and codimension of a simplex is got to be n. And so this says that n plus 1 is greater than C, which says that the minimum core size can't exceed the number of processes. So this is this falls out. This is technical details. So what this says is that for any input simplex sigma, the image of a single simplex under the single round operator is shellable with this dimension. And again, if sigma is a facet, then codimension is 0, then you're talking about C minus 1. So it says that one way to interpret this is that your adversary might have arbitrarily complicated asymmetrical structures. It might fail these two together and those two independently and so on. But in the end, all that matters is the core size. What's the smallest set of processes that can't all fail? That's the only number that affects the connectivity. Oh, so well, we used it here because we needed to show that the pseudosphere is non-empty. So that if what happens is you can always so any set of C minus 1 processes, those could fail, but so what that says, for example, is that there's no asynchronous message passing protocol for C minus 2 set agreement against an adversary with minimum core size C. So that says that if you're interested in a set agreement, this is all you need to know is the minimum core size. Now, what I'm going to show later on is that, in fact, if you're talking about colorless tasks, then the ability to solve k-set agreement completely determines what colorless tasks you can do. So in terms of colorless tasks, it says that the minimum core size completely determines which colorless task can be solved in this model. And in fact, it'll be true in all the models that we look at. Although I don't know, it's probably true for any reasonable model, but I'm not aware of a proof of that. Okay, and that's a statement. So this is a statement about the single round. So here we really take out our microscope and tweezers and look at what happens in a single round of computation. And then because of that general theorem that we proved about the composition, we know that this is true for any number of rounds. Because the adversary doesn't actually fail any processes, he can keep doing this round after round. And so we can go arbitrarily long, and the adversary can keep the protocol complex C-1 connected for as long as it wants. Okay, and this won't be true when we start talking about synchronous models.
But this doesn't prove that every protocol has a satisfying, everything except decision will have an infinite execution. It says it has unbounded.
Yeah, so it says that any finite protocol you give me, I can keep it, the adversary can keep it connected, can prevent it from solving a C-2 set agreement.
So can you pick the limit?
I think you,
Are they somehow, need they be extensions of each other, or can you use Koenig's lemma, saying, taking out of this some graph form which is infinite, and
I think if you can imagine, say, an arbitrary protocol that sort of runs forever, and every now and then somebody raises their hand and says, hey, I've decided. But the thing is, as soon as somebody decides, if they get to send off another round of messages, then everyone else can also decide.
No, I'm asking technically, can you derive from this the idea that you're going to have an infinite non-deciding execution, which you can do from FLP, and you expect that in case of agreement as well.
So you probably can, but there.
You should.
Yeah.
Obviously, it should be
Yeah,
true. The
yeah.
question is whether this is.
Well, the thing is that we've defined these protocol complexes only for finite executions. And I suppose you could define protocol complex for infinite executions, but then it wouldn't be compact anymore. And then things get weird.
No, but the question really is, you have C set agreement, and you have protocols, and
Yeah.
the question is.
Yeah. So,
what
well,
properties will they have?
the
We don't start out from the
Yeah,
point,
yeah.
that's our
Yeah.
aim.
Well, no,
Can
what-
you get a result that every protocol satisfying?
what this gives you for free is for you give me any n, and then I'll give you a computation that fails to solve the problem. Whether taking this to the limit is meaningful, it probably is, but you need to be careful there.
Okay, and there's no theory.
The-
You can't tell me now the theory.
Yeah. I mean, for all I know, it's easy, but you're talking about
Figure it out.
yeah.
Okay.
Yeah, you're talking about infinite limits and non-compact things, and it's an interesting question, though. That
Because one expects that.
you would expect it would be true, but I would also expect that you need to be careful about the definitions. That's the as opposed to being sloppy with the definitions, like we could do with finite. So anyway, this bound is tight. Why is it tight? Find a core of minimum size C, and wait till you hear from one of them, and decide that value. And so this is the size. C different messages might go out. They might get delivered in different orders. As soon as you hear one, you decide that. That's a C set agreement. So that's a tight bound. You can do C set agreement in one round. You can't do C-1 set agreement in any finite number of rounds. Yeah. Okay, so that was the easy one. So now let's move to a synchronous message passing system, where the processes all march in a lockstep, and has the property that the adversary now, instead of making K-set agreement impossible, it wants to postpone it. So in this is a model where a process can crash, but before a process crashes, it can send an arbitrary subset of its messages to other processes. So you can detect failures. I don't get a message from someone on a route. I know they must have crashed, but there's a little bit of uncertainty about exactly when they crashed. So if I don't hear from somebody on round R, it could be they crashed on round R, or it could be that they crashed on round R-1. and still sent, they sent their message and then died, or they didn't. So that's, in some sense, all the uncertainty that you get. And in this model, you can solve a consensus in roughly the number of rounds that there are failures. So of course, you can solve a case set agreement. And so the question is, well, how many rounds does it take? So instead of proving impossibility that you can't ever solve this problem, we want to know what's the lower bound on the number of rounds that you can do. And so you think of the adversary as postponing case set agreement rather than making it impossible. And what we're going to do is we're going to, the adversary is going to fail exactly k processes in each round. And this is why we can't string these round operators together forever, is because eventually we're going to run out of processes to fail. There's a limit on the number of processes that we can fail. So the adversary is going to fail at least k processes and then control the way they send messages to maximize confusion. And again, when a process crashes, the adversary can decide, I'm going to deliver messages to these three, but not to those two, or whatever pattern is the most evil. So here's the protocol. So again, you start out with your state being your input vertex. On round R, you broadcast your previous state, you receive your round R messages, set your state to be the messages received. So it's the same as before, except now we're synchronous instead of asynchronous. And so here, remember we have, here we need a sort of combinatorial structure, which is given a simplex sigma and a face tau. We're interested in all the faces of the simplex between tau and sigma, which is all of the faces that contain tau and are contained in sigma.
Including tau and sigma.
And yeah, including tau and sigma themselves. So this is sort of a partially ordered set, because these two, neither one of these is contained in the other. But this is contained in everything here, and this contains everything there. So you can think of it as a lattice of faces. And what does this, how does this translate into our synchronous model? Well, in every round, there's going to be some set of processes that don't crash. And you must hear from them, because they're non-faulty, they send messages to everyone. And particularly, they're going to send messages to you. Now, processes that do crash, you may or may not hear messages from them. So let's assume that we start out with sigma, and then the adversary fails everyone but tau. The messages that you get are going to be somewhere between tau and sigma. And I might get this one, and Yoram might get that one, for example. And Hagit might get that one. But what we're doing is we're independently choosing a subset that contains the non-faulty sets that is contained in the previous round's non-faulty set. Those are the messages that you're allowed to receive. So writing this down in our notation, this is also a pseudosphere. So we take tau is the face of non-faulty processes. So we're looking at a particular execution where the adversary says, OK, I am not going to fail the processes that are in the input simplex tau. So we start out with sigma. You pick a face and say, this face tau are OK. Everyone else fails. And what does everyone in tau get? Well, you independently hear from some set of processes between tau and sigma. So it could be you hear from everyone who started out, and that's sigma. It could be you hear only from the ones that don't crash, which is tau. Or you could hear from something that contains tau and has some arbitrary collection of other processes that send you messages. And the set that I hear from is independent from the set that someone else hears from. So that's why it's a pseudosphere, because it says that I can independently assign these faces to each of the participants. And then the set of all possible ways you can do this is a pseudosphere. And that's what we get for a specific execution, where we fix the set of non-faulty processes.
How is it different from the pseudosphere we got
So this is different because in the pseudosphere that we got before, what happens is that you could hear from any set of processes that contains a survivor set, but there's lots of, there's more of those. So here, these two have to be the same, in the sense that I'm saying in an execution where tau is non-faulty, who I hear from, it lies between tau and sigma. In the other one, there are no failures, so this is always the simplex sigma, but you might stop waiting for someone because it's asynchronous. So in the previous one, remember, the adversary fails no one, but the adversary withholds messages. Yeah, so the old one is simpler, because this is only the beginning. It's going to get more complicated. So in the old one, it's just sigma, and then you hear from some survivor set. Here, I'm talking about a specific class of executions where I fixed the non-faulty processes. But in fact, the adversary has a choice of non-faulty processes. So the adversary is one execution where tau is non-faulty. There's another set of executions where tau prime is non-faulty. So in fact, what we get is we look at, remember, the adversary fails exactly k processes on each round. And so we're looking at faces tau of codimension k, that is, faces that are missing k vertices, which are the ones who fail. And for each choice, you can choose any of these. So we take a union over all the faces of codimension k, because those are all the possible choices the adversary could make about whom to fail. Then once we fix one of those, then we have the pseudosphere. So the effect of running the synchronous message passing protocol on sigma is, before it was a simple pseudosphere, now we're talking about the union of pseudospheres. So this has a slightly more complicated structure, because instead of having a big pseudosphere that encompasses everything, now we have a union of pseudospheres where each pseudosphere represents a choice the adversary made about whom to fail. Okay, so for each set of n minus k plus 1 non-faulty processes, then each non-faulty process receives messages from all the non-faulty, that's tau, and some, perhaps, of the faulty processes. That's why we're in between. So that's what this expression means. So again, this is just a, writing down with Greek letters the operational model that I gave you about the adversary, failing these and not failing those.
Do you have to remember which processes you failed in the previous operator?
No, because that's implicit in, when you go from one round to another, you throw away the vertices of the failed processes, so the next round operator only operates on the non-faulty processes.
So in the next round, sigma minus tau will not show up, taken away.
Yeah. Tau will show up in the next one, or tau decorated with all the pseudosphere stuff will show up, but sigma is gone. At least some phases of sigma are gone. Okay, so technical restriction is we need n to be larger than 2k. So say for any input simplex sigma, the result of applying the synchronous round operator to sigma is shellable, and we'll spend most of our effort proving that this is in fact a shellable of this dimension. And this is actually trivial technical issue. But proving that this, the image of a single simplex in the round operator that I showed you, the union of pseudospheres is shellable, is where all of the, where we get our exercise. So the proof is that, all the facets, what's it?
If we get exercise there, can we have refreshments before we exercise?
Okay, yeah, actually. What time is it? Okay, yeah, why don't we get